Hello and welcome back to the channel, everyone. This is CCNA Day 15 from NetForge Zone. I'm just going to speak about some more advanced topics in this video. That's going to be what we call it link aggregation. Link aggregation, or bundling links into each other, is going to increase the amount of bandwidth that I can have, and that's going to, help me to forward more traffic than a normal link. Okay, so let's just speak about this. And in this video, I'm just going to speak about the theory. Next video, we are going to see the configuration. Okay, let's just speak about this and why EtherChannel, or what we call it port channeling, or link aggregation exists. Why do we need this? Okay, let's say that, for example, I have some switches here. I'm just going to draw this simple topology again. So in my simple topology, I have these two aggregation switches and multiple let's say access switches. I say aggregation, but you can say that is going to be distribution or aggregation. The names are the same as well. So how we connect them? This is connected to all the distribution switches up here. Same thing on here. Let's say this one and also this one. And also distribution switches are connected to each other. So this is switch 1, switch 2, switch 3, 4, 5, and 6. Okay, and then we have some links up there towards the, let's say, core devices. But what is important for me is this part. Okay, so I have multiple ports on access switches. Say, for example, I have 24 ports on this specific one, and they are connected to multiple devices. Okay, so say, for example, different laptops, cell phones, and stuff like that. Okay, these are going to generate some traffic. How much traffic is going to be generated overall towards access nodes? Say I have 24 ports and they are 1 gigabit per second. So what I'm going to have is something like 2.4, 24 as a matter of fact, not 2.4, 24 gigabit per second of input. If of course all the devices start generating traffic in full load, and of course this doesn't happen, you know that, because mostly you do not really generate so much traffic. But let's say that all of them are going to generate traffic like this. And then one of the links upward is going to be in forward mode. The other one is going to be in, let's say, blocking mode, right? So I have one link up, and this link is going to be something like a 10 gigabit per second link. That's an uplink from the switch with a specific module that is faster than the others. And I don't really have so many uplinks here. Maybe 2, maybe 4, based on the type of switch. And if there, if it is a modular switch, then you can just increase the amount of that. But let's say that I have only 2 of these ports. So when I have one of them connected to here and one of them connected to the other one, so what I have is something like 10 gigabit per second of output. Okay, so what is the overall ratio of input to output in here? My ratio is going to be something like 2.4 to 1, right? That's an okay ratio. We can even increase it when we have some access switches. But if these are not access switches, if these are laptops or end devices, maybe, for example, I have some devices here like file servers that generate a lot of traffic. So what should I do in my case? If there is such thing, what I need to do is to increase the amount of bandwidth that I have here. I add another link between switch 3 and switch 1 to make sure that I can handle this amount of traffic. So say, for example, this is not 24 ports, this is 48 ports. And say I don't have something like 20 gigs of input. I have something like, let's say, 40 gigs of input. And then what I need to do is I need to add some links up here. So what is the problem with this strategy? Say, for example, I have this switch in here and this switch in here. If I have one link between these two switches, everything is all right. Spanning tree comes in here as this. Okay, there is no loop in here, so both sides are going to be in forwarding mode and everything seems to be good. What if I want to increase the amount of bandwidth that I have? I need to add another port in here, right? So when I add another port, then spanning tree sees a loop in here. So it goes and blocks one of these links. Say I have another one. Spanning tree again is going to block another one. So you can see that whatever the number of links are between the two switches, all of them are going to be blocked except one. Why? Because spanning tree blocks them because it thinks that there is a loop in the network. How can I remove these blocked ports, how can I use both of the, for example, in this case, both of these links and make sure that I am using them without having them blocked? There is a mechanism which is called link aggregation. Link aggregation comes here and bundles these two or multiple links that we have into one logical link. So physically they are separate, but logically they are going to be treated as one. Spanning tree sees only one link in here. It doesn't see multiple links. Spanning tree sees one link, so it's going to keep this forwarding, right? So this way I have an added bandwidth in here, which means that in this case, for example, if I bundle these ports, I'm going to use the full capacity of both links up here. Can I use both full capacity? Not really, but we are trained. Okay, so ideally we say that the full capacity of the two links are going to be used, or if I have multiple links, that all of them are going to be used. So spanning tree is going to be fixed with this logical movement, which we call it link aggregation or lag. And sometimes we call it port channeling, sometimes we call it EtherChannel, and link bundling. Different names could be assigned to this, but what we have is link aggregation. Okay, so now we know why we need this. What about the problems that we have with redundant links? So we said that multiple physical links can cause loops. Like I said, spanning tree blocks all of them. So let's say, for example, I have 4 links. 3 of them are going to be blocked. So we are using extra resources on the switches without any outcome. So we can solve the problem. We can use the full bandwidth using link aggregation by bundling link into one logical link, one logical interface. Spanning tree doesn't see physical interfaces anymore. It just sees logical interfaces in this case. Okay, so the benefits. We saw that we needed more bandwidth, so that would be one of them. The other one is going to be link resiliency. Say one of the links go down, the other link is still there, so we can still forward the traffic, although we are going to lose some of the bandwidth, but we are not going to lose the whole link. There are mechanisms that you can define. For example, if I have 4 links between the 2 devices, if even 3 of the links go down, I still keep the remaining link in forwarding mode. So that is what we call it link aggregation. And the other thing is simplified management. When you have multiple interfaces, you need to configure all of them. But when you have one logical interfaces, then you just manage that one logical interface. So the configuration is going to be applied to the members of that logical interface, but basically what you see is that logical interface in here. What about routing protocols and benefits that we have? Okay, so let's see. I can have 2 different types of link aggregation based on the OSI model. So say, for example, I have 2 links between these 2, and I am bundling this. I can have layer 2 aggregation, or I can have layer 3, or let's say layer 2 port channeling, or layer 3 port channeling. If I have layer 2 port channeling, so that's going to be a switch port, it's going to be in switch port mode. You can assign access VLAN to that, or you can assign it as a trunk, and you can use it like you use a normal layer 2 port in here. What if this is an L3 port channel? Doesn't matter. You see again one link between the 2 devices, in this case, for example, switch 1 and switch 2. What you're going to do is to assign an IP address in here and another IP address in here. So this is again one link. You do not see this as 2 separate links. Although in layer 3, you can just ignore this port channel. You can have multiple links between devices, and multiple links between devices is not going to generate any kind of loop in layer 3 if you're cautious, of course. But in layer 2, this is not possible. So if you have one link, then you're going to have one IP address. You're going to have one, let's say, reachability information, or let's say one route. This is going to decrease the amount of information in your routing table. One misconception is very important to understand. Let me go back to here. So I told you that we are going to increase bandwidth. we have two concepts. One of them is going to be bandwidth, one of them is going to be speed. Let me just give you an analogy. So say this is a road, okay? And there is a speed limit of something like 70 mph. This means that cars cannot drive faster than 70 miles per hour, right? So if there is one lane, so all the cars have to obey this and they cannot really go faster than that. And like I said, if this is one lane, so each cars could have to go like this. All of them are going to follow each other. What if I have multiple lanes? Say, for example, this is a highway, and I have, let's say, one lane in here, one lane in here, and one lane in here, which means that this is a 4-lane highway. So speed limit is still 70 mph, right? But now at the same time, you can have 4 cars driving at any parts of the highway, which means that we can increase the amount of throughput 4 times because now we have 4 different links, same things as what we have in here. So if I have 2 switches in here, if there's only one link, speed is the same. So the amount of packets that go through this is going to be 1 time. But if I have multiple links, then I'm going to have 3 times, 4 times more packets through the links, and that is going to increase the bandwidth. So what is the difference between the speed and bandwidth? Like I said, the speed is going to be like this. The speed that signals can go from one side of the wire to the other side, or one side of the fiber to the other side, or maybe if you are talking about wireless technology, from one station to the other station, that's going to be a safe speed. But the number of packets that you can send at the same time through different links, that's going to be your bandwidth. So bandwidth is going to increase or decrease, and this means that you can send more information or less information at any given time. So this is very important to understand, right? So let's go back to here. Again, there are multiple ways to configure this. And basically there are 2 ways, static and dynamic. What is the difference between these two? So when you configure a static link aggregation, one side only knows about itself. So say one more time, I have this switch in here and this switch in here, and we have this is very ugly actually. Let me just draw it more time. So this is in here, and I have 2 links in here. So switch 1 and switch 2 are going to configure link aggregation. They can either talk to each other to create a bundle out of these 2 links, or they can do it separately. If they do it separately, this means that we are using static mode. What is the problem with that? Do you remember when I talked about static trunking or dynamic trunking? I told you that when we have dynamic trunking, both sides negotiate with each other, and then they decide that the link between them is going to be trunk. When we have a static trunking, each side is going to assume that there is a trunking between, and the link is going to be treated as a trunk. But if the other side doesn't create the trunk, this side is not going to be able to use it. If there is a negotiation, it will know that the other side is not a trunk to not use the link. But if there is no negotiation, it uses the link as a trunk without knowing that there is a problem on the other side. Such thing happens in here. So if you say, for example, I'm configuring static link aggregation, I treat both links as one logical link, and then I try to send information of both of them. If the other side has not been configured with a port channel, then the other side is going to block one of the links, basically, because it will say, okay, a spanning tree says, I need to block one of the links. So you are going to miss a lot of packets as though the link is not going to work properly. You're going to lose a lot of packets actually. So what you need to do is to go with dynamic. So basically sometimes you configure static, but because you don't have any information whether the other side is working or not, this is going to cause some problems in case of let's say failures. But when you see dynamic means that there should be a negotiation. Okay, negotiation takes time, convergence is going to take time, but sometimes you really need this. Let's say in data center, for example, using dynamic is more preferable over static because we want to know what is the state of the link from the other side. So we want to have kind of a negotiation. So in this case, what you are going to do is to use dynamic link aggregation. In dynamic link aggregation, you talk to the other side. And there are different modes that I'm going to speak about this, but two actual protocols are in place. One of them is standard, and Cisco prefers this one. The other one is Cisco proprietary, but because the standard has been generated from Cisco's protocol, so I prefer the standard one, LACP. So LACP and PAgP, these two are almost similar. They have some kind of a negotiation with the other side, and then they, if the negotiation goes fine, then this is going to work. So what are each one of them? PAgP, Port Aggregation Protocol. So this is Cisco proprietary. This means that only Cisco switches know that. There are two modes. One of them is auto and one of them is desirable. And you do not really need to know this for a CCNA. But let's see how this is going to work. If switch 1 is auto, this means that I'm not going to create a port channel unless you ask me. I am here sitting for myself. I'm not going to do anything unless I am asked to do that. So if side 1 is switch 1, for example, is being configured with auto and switch 2 is configured with auto, none of them is going to start a negotiation with the other side. No link aggregation is going to be generated in here. The other type is desirable. So desirable means that I actively want to create the port channel. So I start negotiation. I send you messages. Okay, I told you that if there is an auto configuration on the other side, auto says I'm not doing anything unless you ask me. So desirable asks it. So if one side is desirable and the other side is being configured with auto, this means that we are going to have a port channel. Okay, what about this scenario? One side is desirable, the other side is desirable. Both of them are actively seeking a port channel. So this is going to work. So you can see that in this case, if both sides are configured as auto, none of them is going to start negotiation and no port channel is going to be created between the two switches that we have. That is very important. But like I said, this is not required with for CCNA. You don't need to know about this. What about LACP? Now, LACP, like I said, is vendor neutral. This means that you can have multiple devices from different vendors, different manufacturers, and they can create a port channel. And that is what a standard means. A standard means that multiple manufacturers understand that. Okay, so what are the modes in here? In here, what we have is called active mode and passive mode. Okay, so again, if switch 1 is passive and switch 2 is passive, again, like auto, as I told you, none of them is going to start the negotiations, or nobody will create a port channel. If one of them is active, the other one is passive. Like I said, passive says, I'm not going to do anything unless you ask me. So this is going to generate, because active really wants the other side, starts a negotiation with the other side to generate this port channel. And if both of them are active, again, because both of them wants to create a port channel, this is going to work. What is important is the number of links that you can use to create a port channel. Based on the device, of course, this is going to be different. Normally, you can go from 2 to 8. I have seen 16 on some bigger platforms, but in CCNA book, of course, it says 2 to 8, so you need to know this. So negotiation is going to be there. With negotiation, we can understand that, well, if we are going to create this or not. I spoke about different nodes, like I said, active and passive. Active initiates, passive responds. So passive is not going to do anything unless it is asked. So passive, like I said, is not going to generate anything for you. So no port channel is going to be created unless at least one side is active. Okay, so there are rules actually. You cannot really bundle any port with any port. You should have ports that have the same speed and duplex configuration. So if I have a 10 gigabit per second and a 1 gigabit per second link, I cannot put them into the same into a link aggregation. What I need to do is to make sure that both of them are, let's say, 10 gigabit per second or 1 gigabit per second. Both of them are have to place or full replace. Both of them have the same configuration. If, for example, one of them is trunk, the other one is access, this is not going to work. If both of them are trunk, they should have the same VLANs allowed on them. If one of them says VLAN, for example, 10 is not allowed, the other one says 10 is allowed, this is not going to work. So configuration should be the same. Be very careful about this. And this is a requirement. And there are some other requirements actually, but these are the most important that you need to know. And finally, we have load balancing. So load balancing is not going to be perfect. I told you that if you have this switch in here and this switch in here, if you have two links, each one of them at 10 gigabit per second, of course this one is very crooked, but okay, now this is a bit. If these two have two links, each one of them 10 gigabit per second in here, this is not going to give you a 20 gigabit per second. Is it gonna be 20 gigabit per second? So this means that 10 plus 10 is going to be almost 20. It is not really 20. Why? Okay, this is one logical link, yes, but switch knows that this is two physical links. When switch wants to put data on that, the switch doesn't put data on logical things, it just puts it on physical links. And switch decides how it is going to use each one of the links for a specific flow. What is a flow? A flow is a number of packets. You know packets? Packet is data unit in layer 3. Frame is data unit in layer 2. Remember? And segment is data unit in layer 4. So a packet has a source and destination IP address. Packet has a source and destination MAC address. And packet has protocol number or a port number, right? So we have 1, 2, 3, 4, and 5 pieces of information. So we call it 5 tuple. 5 tuple, right? So 5 tuples actually. So this is going to define a flow. Every packet that has these 5 tuples, the same is going to be put into one flow. So let's say, for example, I have a packet from 10, 1, 1, 201 to, let's say, 192, 168, 1, 209. This is a source, this is a destination. The MAC address is, for example, let's say this is A, something like that. And the destination MAC address is like B, something like that, whatever. And then this is, let's say, an IP packet, and the port number is, let's say, 443. Okay, so you can see 5 pieces of information. This is going to be a flow. So my flow, in this case, for example, it is HTTPS flow, right? So this is one flow. Every packet that is generated from this address to this address, with this MAC address to this MAC address, with this port number, all of them are going to be in the same flow. Okay, are the flows the same size? Actually, no. So sometimes based on some hashing mechanism, the switch is going to decide this flow is going to go on this, the other flow is going to go on this. Some of the flows are called elephant flows. Let's say, for example, you are downloading a 10 gigabit file that is from the same source to the same destination, but 10 gigabits of data. Some of them are called a mouse flow. Let's say, for example, an HTTP request. It is very small packet, right? Or HTTP response. It's going to be something like 2, 3, 5 megabits. Not more than that, right? So sometimes you can see that one of the links is utilized to the full, the other one is totally empty. That is because we have some flows that are going to, utilize the link to the full capacity, but on the other link, for example, you do not really see many flows. And if we have multiple links, of course, it's going to be the same thing, right? So be very careful about this. Load balancing is not always the best method to, use the links. So what I told you is, if you just bundle two 10 gigabits per second or 40 10 gigabits per second, it's not going to give you 20 or 40 gigabits per second link. It is just going to increase your bandwidth. Now, very much similar to the highway. On some of the lanes, we can have more cars than the other lanes, but same thing goes in here. In the next video, I'm just going to show you how you can configure this. Thank you for watching. If you like this, press that thumbs up. And also hit the bell button and subscribe to the channel, and see you in later videos.